In the last session, we have seen the implementation of stack using linked list, and in today's session, we'll see how to implement a queue using linked list. So here also, we'll be making use of single linked list for implementing queue. Now, in stack, what we did that while implementing a stack, we knew that there's only one end which is called as the top of a stack, and from this top end only the insertion and the deletion is done, which is also called as push and pop. But for the queue, as we all know, that in a stack there is only one open end, but in a queue there are two open ends, right? So from one end the data is inserted, and from another end the data is deleted. So the end from where the data is deleted is called the front end of a queue, and the end from where the data is inserted is called as the rear end of a queue. Okay, so basically we need to preserve two ends in a queue, and to preserve two ends in a queue, while we implemented the queue using arrays, what we did, we had two indices or two variables for storing the index value. One was front, another was rear, and the front used to store the index value of the frontmost element of a queue, and rear used to store the index value of the last element of a queue. Okay, so in that way we implemented using arrays. But when we talk about implementing a queue using list, so now we can understand that we need to preserve two pointers. Now, while we implemented stack using list, we had only one pointer called at the top of a stack, and basically the head pointer of a list was renamed as top pointer, and we used that pointer itself as a top pointer. Okay, so that way we did implementation of stack. But when we talk about implementation of a queue, so we need to understand that we need to preserve two pointers. One is the pointer, which is your front pointer, and another is your rear pointer. So your front pointer, if I talk from a list perspective, so the front pointer will be always pointing to the first node of uh, of a list, and the rear pointer would be always pointing to the last node of a list. Okay, and then whenever I want to insert, I would be inserting from the rear end, that is insert at end. And whenever I want to delete, so I would be deleting from the front end. Okay, so that is nothing but remove first. Fine. So when we compared the push and pop functions with the insert and remove functions of SLL, so we could easily see that push function resembles the insert at beginning of SLL, and the pop function resembled remove first. Okay, because there was only one end. So from beginning only or from first only you need to insert and delete. Okay, so it was insert at beginning and remove first. But when you talk about queue, so we have two ends. Fine. So one operation, that is insertion, would be done from one end, and the delete operation or the remove operation would be done from another end. Fine. The operation from where the insertion is done is your rear end, and the operation from where your deletion is done is called the front end. Now, if I visualize that my front is always pointing to the first node, so definitely my rear is pointing to the last node. When rear is pointing to the last node, front is pointing to the first node. So whenever I want to insert, I would be inserting from the rear end. So it is nothing but insert at end. I repeat, insert at end. Okay. So the insert operation of queue resembles the insert at end function of SLL. Likewise, if I want to delete, so I would be deleting always from the front end. I would be deleting from the front end. Okay. So the delete operation of a queue resembles remove first of a SLL. I repeat, the delete operation of a queue resembles the remove first function of a single linked list. Okay. So this way now it becomes quite easy and straightforward for us to implement a queue using linked list. Now, what I have done into this program, if you see, so this is nothing but something like a node structure. I named it SLL. You can name it node or you can name it whatever you want, but it should be valid and logical. Then after this node structure, what we can see that there is one more structure, and this structure is basically having two pointers, the front pointer and the rear pointer. And these pointers are going to point to the nodes. So the type of the pointers would be the structure node pointer. So now in this case, our node structure name is SLL, and that's why the front and rear both becomes a pointer to structure SLL, and here also pointer to structure SLL. Okay, and they are combined, or they are confined to one structure, and that structure we have named as Q. Okay. Now, why did we do this? Now, this is only to make our program little abstracted, or I can say to make the program little generalized. Okay. Now, these are the few small things by which what we try to do. We try to keep the program more and more clean. What I mean to say that we do not throw out our pointers or our important stuff here and there. We combine them into something. We combine them into one block. We combine them into one structure. And then whenever we want to use them, we just declare the variable of this structure. We declare the pointer of this structure, and then we use them. Okay. So they are basically encapsulated in terms of programming, and in terms of computer science, we call this as encapsulation. I'm quite sure that you must have studied this concept of encapsulation in object-oriented programming. So basically, this is a better approach. By this, what we do, we make our code more and more cleaner, and we do not allow the things to move here and there. We encapsulate the things, we structure them, and we keep them bounded together. Okay, and that way, whenever we want to use them, we simply make use of a variable or a pointer or the object of this specific type, and then we use them. Okay. So if we do not do this, then what we would have been doing, we would be creating the two pointers, front and rear, in the main function, as we did for the stack. What we did for the stack, we created a top pointer in the main function itself. Now there, it was okay. Why it was okay? Because there was one pointer for one stack. I repeat, there was one pointer for one stack. So I declared a top as a pointer to a stack, and that gives me one stack. I declared two variables, top one, top two. It gives. I declared two pointers, top one and top two, and it would have given me two stacks. And likewise. But if I talk about queue, then for every queue, you need to maintain two pointers. Please try to understand. Okay, there's always a trade-off. Trade-off means compromising the things between two, which are something like indirectly proportional to one another. If one thing increases, then other thing decreases, and if other thing increases, then this thing decreases. So you need to balance them out. So that is called trade-off. Okay. So now we have two pointers. So we cannot allow a program wherein in the main function to have a single queue, you will be having two pointers. Then if you want to maintain two queue, then you will be having four pointers. If you maintain three queue, then you will be having six pointers. So that's not expected, that's not feasible. And then our code won't be clean. If I don't understand, the code won't be clean. Your main function will be jumbled out of so many pointers and so on. So the cleaner idea, the better idea is to encapsulate the two pointers in a single structure, in a single block, and then as and when required, just declare the variable or a pointer of this structure type, and start making use of a queue. So what we'll be doing, we'll be either having a pointer to this structure, or a pointer to this structure queue, or we can have a variable of this structure queue, and that single variable or a single pointer will give you single queue. If you have two variables or two pointers, you will be getting two queues. If you have n number of those variables or those pointers, then you'll be getting n number of queues. Okay. So this way we are making it simpler, and this way we are making it cleaner. Yes, it does come with some complications or complexity, and the complexity is not bigger. You have one additional structure that's all done. So if we understand the structure, if we understand the pointer, it's a way simple thing for us. Okay, so only with the help of one additional structure, we are now able to make our code more cleaner, to make our program more cleaner and more simpler. Okay, let's see how we are making use of a queue. Now I directly go to the main function, and there we'll see. Yes. So now you can see here, I have one pointer, a pointer queue to a structure queue. And this single pointer would give me one queue. If I want to access the front pointer of this queue, then I would be writing queue arrow operator front. If I want to access the rear pointer of this queue, then I would be writing queue arrow operator rear. Or in short, indirectly, I can also say that if I want the frontmost element of this queue, then I can simply access that frontmost element by writing queue arrow operator front. And if I want the data of that, then queue arrow operator front arrow operator data. If I want the data of the last element of a queue, then I would be writing queue arrow operator rear arrow operator data. So that way I can directly access the data of the frontmost element. I can directly access the data of the last element. Likewise, I can access the next pointer of the frontmost element. I can access the next pointer of the last element, like that. One additional stuff, which is important to understand, we have is this. In earlier programs, whenever we had a head pointer, or in case of your implementation of stack using list, the top pointer. So for any linked list, whenever we had a head pointer, we did not allocate a space to that head pointer. Please make a note of this. I repeat, we did not allocate a memory to a head pointer. Okay. What we did, we declared the head pointer. We directly initialized the head pointer with a null value. So head equals to null. So that was the initialization of a list, whether it's a SLL, whether it's CLL, or whether it's DLL, no matter. It doesn't matter. Okay. What we did, we directly initialized the pointer, that is head equals to null, and then we started using it. In this case specifically, what we are doing, we understand that Q is something like my head pointer, because this small q, this single small q would give me one q. Likewise, if I had one more pointer to a structure q, then that would give me another q, and so on. So they are something like our head pointers for the q. But now in this program, what we are doing, we are allocating a space to this something like a head pointer. So can you tell me why we are doing this? Any idea why we are writing q equals to struct q star, then malloc, then size of struct q? Any student, please. This is basically what we used to do whenever we wanted to create any node. So whenever we wanted to create any node, we used to write like this: p equals to struct SLL star, then malloc size of struct SLL, something like that. Why we are doing this over here? Come on, fast. Please post your answer. Yes, what's the reason? We need to allocate a memory for it. Yes, we need to allocate a memory for it, but why we are allocating a memory? That's my question. The question is why we are allocating a memory? Why we are doing this? We did not do this earlier in any linked list, even in the implementation of stack. We did not write top equals to uh, struct stack star malloc size of struct stack. We did not write like that. But here for Q we are writing. What's the reason? Come on, no answer. Here at the end we have to implement SLL, and before we simply implemented Q. I'm not getting it. There's one answer because there are two opponents. Mm, Then, in fact, if you see carefully, so you should get the answer from the very next statement. Okay, now let me explain. We waited for around a minute, and we got few answers which are not exactly what is expected. They are a little here and there, but related. I'm getting one more answer because we are creating node that stores data as well as address of next data. Okay, now Alfia is correct that we are creating node that stores data as well as address of next data. So yes, but again, not exactly to this, but she's far close to the answer. The point is what you know. Please try to understand this. When you declare a pointer, so what happens? Basically, two possibilities. We make use of a pointer to hold the address of something so that my pointer can point to something, okay, in the memory. For example, this is my memory and these are my memory blocks, something like that. And when I got a pointer, and if that pointer points to something, so I can indirectly access this memory block with the help of my pointer. I can indirectly access this memory block with the help of my pointer. In this case, I may not need to allocate a space to my pointer. I repeat, I may not need to allocate a space to my pointer because my pointer is only going to hold the address of this memory block, which is pointed by something else or which is referred by something else. And this is my additional pointer. And through this additional pointer, I can access indirectly. I can access indirectly this block. Okay. So this pointer is going to hold only the address. Now, if for some reason I not only want this pointer to hold an address, because I want this pointer to hold an address of entire block, and that entire block can be referred with the help of this pointer. So there I need to allocate a space. Okay. Or in short, what I need to say that this pointer is going to have something else into them or into it, which can have value. For example, this pointer q is going to have two pointers in itself. So this pointer q is going to hold up some space. some memory block. In that memory block, there are again two pointers. One is your front and another one is your rear. So you need a space, this much space for this pointer. Okay. So this pointer is not going to just hold the address of any memory block. This is going to hold a address of a block, which is again going to hold up two pointers, the front pointer and the rear pointer, which are going to have the address of some nodes. Okay. The front pointer will be having the address of the frontmost or the first node of the queue. The rear pointer would be having the address of the last node of a queue. Okay. And then these two pointers are encapsulated together in a block, and that block is basically pointed by the pointer q. So basically, I need a block, I need a space where we can keep the front pointer and the rear pointer. I repeat, we need a space, we need a block. And since we need a space, we need a block of memory. So for that purpose, we are allocating a memory. Otherwise, in case of a head pointer, or even in a case of top pointer, we did not require this. What we did for a head pointer, the head pointer will be always storing just the address of the first node, always pointing to the first node. The first node has been created with the help of another pointer, p equals to malloc, if you remember. Likewise, in case of stack also. Okay, so here we need a memory block. We need a space wherein we can store the front pointer and the rear pointer. And then this block would be pointed by my pointer q. And that's why we have this statement q equals to struct q star malloc size of struct q. Okay. And then only we could write this. If you do not have this, if I remove this, then I cannot write this. Q of front equals to Q of rear equals to null. This is not accessible. This is not done. The space has not been created. So where I would be putting this null value? Front and rear are the data members of a structure to which the Q is a pointer. But if I do not have a space, so where I would be putting this null value? So for that, I need to create a space, and then only I can write equals to something. If you have space, then only you can assign up a value. Then only you can store a value, whichever value, null value, any address, any data of any type. So you need a space. And for that, we need to allocate a space to a pointer q. Only after this allocation, you can write up this statement. Q equals to, Q of front equals to Q of rear equals to null. So basically now this is my initialization of a Q, which is pointed by the pointer small q. Okay. So this is my initialization of a Q, where I am writing Q of front equals to Q of rear equals to null. Okay. And in case of stack, what did we write? Top equals to null. So that was the initialization of a stack. Now you could say that there we could write top equals to null without allocating a space. So why we cannot write the same thing over here? Because front and rear are the members of a structure. They are inside the structure. Top was simply a pointer to that structure. Likewise, here Q is a pointer to a structure. I can simply write Q equals to null. No issue about that, without allocating a space to a pointer Q. But I want to access the data members which are inside the structure using the pointer Q. That's why I need to allocate a space to Q. I hope you are getting it now. So this is my initialization of a Q. Initialization of Q pointed by this small Q. Okay. Then we have our infinite loop, menu-driven program, where we have the option for insert, delete, and then we have put one more option of searching a given node, then displaying the queue and exit. So in insert, we are calling the insert function, and the style is same. the head pointer equals to the name of a function in parentheses head pointer comma the data. Okay. Likewise for delete, the style is same, just like your remove function. Head pointer equals to function name in parentheses the head pointer. Okay. So here it is q equals to insert, then in parentheses q comma d, and likewise for delete, q equals to delete in parentheses q. Then for search, mm, I will let you know how the search is working. So let's move to the insert function. Now this insert function is equivalent to what? Can you tell me? I already told you. This insert function of a queue resembles which function of SLL? Come on, fast. We don't have much time. Insert is from which end? Where end? So this will resemble which function of SLL? Insert at beginning, insert at end, or insert after, or insert before? Which function? Insert at end, and someone is saying insert at beginning. Why insert at beginning? It should be insert at end. You have two ends, the front end and the rear end. Front end is pointing to the first element, first node. Rear end is pointing to the last node. So your insertion would be always done from the rear end, and it is pointing to the last node. So your insert is insert at end. Okay. Your delete is basically delete first. Deletion is done from the front end. So it would be remove first. Fine. So this is now insert at end. This is insert at end. So we allocate a space. Then this should be SLL for your fine information. And then if P is null, then only I can say my queue is full. Okay. Just like your stack. When a memory cannot be allocated for any reason, then only we say that the structure is full. Else, we make up the node P of data equals to D, P of next equals to null, and see here carefully. We are not at all traversing, though it is insert at end, but we need not have to traverse. Why we need not have to traverse? Because the last node pointer we already have with us. That is the rear pointer. So rear is pointing to the last node. Now this node is going to be a new last node. So with the help of that rear pointer, we can easily make up it. So what we are doing, if my q of front is null, then q of front equals to p. And if q of rear not equals to null, q of rear of next equals to p, and then q of rear equals to p. So can you tell me what does it mean when I write q of front equals to null? It simply means that if q is empty, if q is empty. So if my queue is empty, so it means that my front and rear pointer both are null. I can check for any one pointer. I'm checking here for front. So if my queue of front is null, my queue is empty. So this becomes my first node. The P is going to be the first node, and that's why we are saying queue of front equals to P. That's why we are saying queue of front equals to P. Okay, this is done. This is nothing but something like if H equals to null, then H equals to P, if you remember. So if our list is empty, so H would be null. So if H equals to null, this node is going to be the first node. So we used to write H equals to P. Exactly, same like that. Here we are checking for the front pointer. Or in fact, we can check for the rear pointer also. So if my queue of front equals to null, it means that my queue is empty. And in that case, this node is going to be my first node. And that's why my front pointer should be pointing to this node. And that's why we write queue of front equals to P. Okay. After that, we are writing if queue of rear not equals to null. If queue of rear not equals to null. Can you tell me what does it mean? Come on, fast. We do not have time. Think. Post me an answer. Q of rear not equals to null. What does it mean? When I say queue of run equals to null, it means queue is empty. So when queue of there not equals to null, it means what? If there is something in queue is not empty. Okay, good. So it simply means that only. It means that there are some nodes in a queue. There is something in the queue. Okay. So my queue of there is not equals to null. Now, why do we have this check? Please see here carefully after this. If there is something in my queue, so my where pointer is already pointing to the last node. If there are some nodes in my queue, so my where pointer would be pointing to the last node. Now my where pointer is pointing to the last node. This node, a new node, is now going to be a last node. So the next pointer of that last node should point to P. I repeat, the next pointer of the last node should be pointing to P. Last node is pointed by Q of where? Last node is pointed by Q of there. So we write Q of there. And then its next pointer of the last node. So by writing arrow operator next, we get the next pointer of that last node, which is null because this is SLL. Okay? So if my Q of where of next is null, now I need to set that to P so that my P becomes a last node or P gets attached to my list. And that's why we write equals to P. Done. Now, since this is done, after this statement, I need to modify my where pointer because now P is the last node, new last node. So my where pointer should be pointing to P. So I simply write Q of where equals to P. Are you getting it? Q of where equals to P. Okay? So this Q of where not equals to null, it simply means there is something in Q. Or I can say Q has data or Q has node. Q has nodes, I can say. Or something like Q has data. So since Q has nodes, so what I need a next pointer of the last node. Please see here. What I need the next pointer of the last node. The last node is pointed by Q of where. And that's why I would be writing Q of where. And then its next pointer. And that's why as operator next equals to this new node. So that my new node gets attached to my list. Okay, and now the new node is becoming a last node, and since my new node is becoming a last node, that I can do by writing Q of where equals to P. Okay, so this is attaching new node to the last node. Okay, and then making new node as last node. Okay, so this statement is nothing, making a new node as a last node, and this statement is attaching new node to the last node. Be careful that only this statement is a part of if. If this condition is true, then only you will be executing this statement. Okay. So inside if you have only this single statement because there is no opening, closing curly braces. Okay. So if there is something in the queue, then only you will be attaching a new node to the last node. If there is no last node, if there is nothing in the queue, and this node is going to be the first node, then in that case, we'll simply say Q of where equals to P. Okay. So this node would become simply a last. Attaching new node to the last node, or I can say new node to the list or to the queue. Okay. Then returning the queue pointer, the else part only. Display function is there, and let me first explain the delete, and let us do it fast. We are running out of time. Delete function is simply you need to delete the first node with the help of the front pointer. So here we are checking if any of the pointer, rear pointer or the front pointer is null. If any of the pointer is null, then I simply say queue is empty. Else, if the queue is not empty, if there is something in the queue, then only we can perform the delete operation. So first thing I'm printing out that the deleted element, the deletion is done from the front end. So the element which I am going to delete, the data of the deleted element would be queue of front of data. So that's what we are doing here, queue of front of data. Okay. Then I'm taking it into a temporary pointer. So temp equals to queue of front. And then I'm modifying the front pointer so that now front should be pointing to the second node. Okay, because I want to delete the first node. So queue of front equals to queue of front of next. It is as simple as that. Something like h equals to h of next. So here your h is basically queue of front. Your h is what? Queue of front. So queue of front equals to queue of front of next. Okay. Then if queue of front equals null, after this, if my queue of front becomes null, it means that this was the last element, or this was the only element in my queue. I have deleted that element, so I need to make my rear pointer also null. Okay. So if queue of front equals null, if my front has become null, so I would rear also null. So queue of rear equals to null, and then setting the next pointer of my temp is pointing to the next node. If queue gets empty, if queue gets empty after deleting deleting a node, or after removing a node, whatever you want to call it, just understand what I am saying. So in that case, we'll make up the rear pointer also null, and this is uh, to make your front pointer to point to the next node, which can also be null. So make front to point to next node. Okay, fine. So this way your delete function would work. It is quite straightforward. Now, since you have two pointers, I repeat, the front pointer and the rear pointer, so you did not have to traverse either in the insert operation or for the delete operation. But yes, for the displaying, you need to traverse, and for searching also, you need to traverse. So let's get back to the display function. We'll be starting from the front end and we'll be going up to the rear end. Okay. So first checking for the empty condition. If my queue is empty, so we'll be simply saying the queue is empty. If any of the pointer is null, else one dummy pointer, then displaying out the queue content. And here I'm making use of a for statement instead of a while. And I'm starting from the front pointer. So temp equals to queue of front, temp not equals to null, because the last node's next pointer is going to be null. This is implementing queue using SLL. So the last node next pointer would be null. So temp not equals to null, temp equals to temp of next. Okay. And inside the loop, I am writing printf percentage %d temp of data. Now this for statement is exactly similar to your while statement, where you write first temp equals to queue of front, and then while temp not equals to null, and then inside it print slash printf slash and percentage %d comma temp of data, and then after that temp equals to temp of data, temp of next. Okay, so this for statement is exactly similar to your while loop. So this will display out, and then you have a search function. Now this search function is also a good way Now the searching is exactly same the way we used to do inside any function, like insert after, insert before, remove after, remove before. Okay. The condition used to be while temp not equals to null, and at the same time temp of data not equals to k or not equals to key. Okay. And that's what we are doing here. Temp while temp not equals to null, and at the same time temp of data not equals to key, temp equals to temp of next. Fine. And then we are simply returning 10. So basically what we are doing into this function, we are returning a pointer to a node which consists of the given data. So we are searching for the node which consists of a given data. So we are searching for the given data or the given key value. If the key value exists, then it will return the pointer to a node where the key value exists. And if the key value does not exist, then it will return a null value. I repeat, if the key value does not exist, then it will return a null. If the key value exists, then it will return the pointer to that node in which the key value is present. Okay. So this is your search function, and this is a good way of implementing a search function. So returning a pointer to a structure SLL, and it accepts a pointer to a queue. See there carefully. It is accepting a pointer to a queue and returning a pointer to SLL because the node is of type struct SLL star, then accepting a key value of int type, and then if the queue is empty, so we cannot search for anything, so we are checking for an empty queue. Else, we are starting from the first node, so temp equals to queue of front, and then while temp not equals to null, and at the same time temp of data not equals to key, temp equals to temp of next. Simply that. The moment the node is found, it will come out of a loop. I repeat, the moment the node is found, it will come out of a loop. And if the node does not exist, then it will completely traverse the list. And finally, when it comes out of a loop, the value of temp would be null because it would be reaching to the next of the last node, and the next of the last node is null. So if the value is not found, if the value does not exist, then after this loop, the value of this temp would be null. So null will be returned. And if the value exists, then the moment the value is found, it will come out of a loop because the condition would fail. Temp of data would become equal to key. So if the key is found, then it will come out of a loop. And when it comes out of a loop, the temp would be pointing to that node. Temp would be having the address of that node, and now we are returning the address of that node or the location of that node. Okay. So this way, this simple return statement would take care of both the things, null also and address also. And how we are using that search function? Here in this case, third case, we are asking for the data, then we are scanning a data, then we are calling the search function. See how we are calling the search function. K equals to, now K is a pointer over here of type struct SLL. So K equals to search Q comma D. If K equals null, if the return value is null, then the key value does not exist. So key is not found. Else printf key is found having a value. So now we are displaying the value of data, K of data. Okay? So this way you can display the data, or you can even display key is found and is present at location percentage X, and then you can simply display the address by writing K. So simply by writing a K, you can display the address. Okay, so this way your queue is implemented using list. I simply execute it once and show you the execution part. Insert. So I want to insert something. I insert say 10. 10 is inserted. I insert 20, and then I insert 30. And if I display my queue, so it is displayed from the front end, and at the front you have 10, and then 20, and then 30. First in, first out. Now, if I delete for the second option, then the first element, the element which was inserted first in, first out before, would be deleted first. So 10 was inserted first, so 10 got deleted first. Okay, so the deleted element is 10. And if I want to search, now I'm searching for the say 10, which has been deleted. So it says me key element or the key is not found. 10 is not present in our queue. I go for one more search and I want to search say 30. So it says me yes, key is found having a value 30. Okay. So that is also working properly. If I delete one more element, 20 got deleted. I delete once again, 30 got deleted. I try to delete again and now the queue is empty. So it gives me a message, queue is empty. Now again, I can perform some insert operation and I can do all those stuff. Okay. So this is the implementation of queue using list. If you have any questions, you can post your questions or we can have a discussion on that. I stop the recording meanwhile. I'll